Welcome to day 16 of the 2024 Advent of Code. We have what seems to be the 500th grid problem this year. We have a map again and a reindeer on a starting tile labeled S facing east, which is right, and an end tile, and the reindeer needs to get from the start to the end. We want to get the lowest score, so you can imagine that as time, and moving forward is an increase of 1 point, and obviously you cannot go into walls, and you can rotate counterclockwise or clockwise 90 degrees, which costs 1,000 points. So this is the example map, and we basically just want to see what the lowest possible score we could get is. So this is a simple Dijkstra problem. Let me briefly explain. So previously we've used breadth first search this year. So as an example, let's suppose we are trying to pathfind to this here from here as a starting point. So in breadth first search, what we did was we basically put things into a queue. So we start with queuing this object, and then each time we look at the next item in the queue, look at its neighbors, and then add those into the queue in whatever order. And then we take another one off, look at its neighbors, add any that have not been seen yet to the queue, so this one doesn't get added. And then we look at the next item in the queue, which would be this one. And then this would let us find the destination, which means that we would stop here and get a score of 2. Now in Dijkstra, this changes a bit because the Dijkstra is basically used when the edges have different costs. So in this case, let's suppose that we have these possible actions. We have a move that costs 2, a move that costs 3, a move that costs 10, a move that costs 1, and a move that costs 5. So in this case, what we do is instead of just adding them into a queue, we have to go through them from the lowest cost to the highest cost, because we need to make sure that we find the lowest cost way to get here, not the shortest number of edges. So we would queue this, and then when we look at this node, we'd look at its neighbors. We see that this one's cheapest, so it gets added first. And then when we look at this, we see that we can get to our destination with a cost of 12. Let me label these with the costs instead. However, we note that this clearly is not the cheapest way to get there. So unlike in breadth first search, we don't stop when we see the node, we stop when we actually visit it. So because this is not the cheapest, we revisit this node. Or rather, we don't know that this is not the cheapest, but we have to keep going. This has a cost of 4. And then we go here, which has a cost of 9. And so we would look at this first before looking at this case, because this one is closer. So how can we do that? Even though we inserted the 12th case first, we need to look at the 9th case first. So basically this is not an actual queue anymore, because the first item we insert is not the first item we look at. Rather, each time we have some mysterious black box, we're putting items in some order that is not lowest to highest, and we want to pull out the lowest number each time. How can we do that? Well, there is a data structure called a priority queue, which does exactly this. The interface requirements of a priority queue is that you can insert any item into it, and you can take the lowest item out of it. That is basically the purpose of a priority queue. There are a couple of implementations for this. The most common one is a heap, which is a data structure that keeps everything in a layered tree where the top element is the lowest and each element is lower than its descendants. But we won't go into the implementation details here, as that would be a topic for another video. So we need to import the heap queue library in Python, which is the Python library for priority queues. The two functions that we use in this are heap push and heap pop. Here are the possible ones. Heapify is a function that takes a list and converts it into heap order. Heap pop takes a list and returns the smallest element. It must be in heap order. Heap push takes a list that's in heap order and adds another item into it, such that the remaining item stays in a heap order. Heap push pop takes in an item and gives you the smallest item. This one is a bit more efficient for than doing two separate operations. And the rest of these I don't really know because you never really use them. Heap pop and heap push are the only two that really ever get used in my experience. So let's proceed with grabbing our input. And now that we have our grid, let's set up our Dijkstra's algorithm. So we need to have our priority queue to tell us where to start. Notably, we do not want, in breadth first search, when we see a node for the first time, we mark it off as seen. So for example, we start here, we see this node, so we mark it as seen. We go here, and then even if we look at this, we see that we've already added it, so we don't add it again. But in Dijkstra, again, remember that the first time we see a node might not be the cheapest time. So the only time we mark a node as seen is when we actually process it and not when we add it. So we will have our priority queue, or I'm getting ahead of myself. We need to first look for the start and end points. So that'll get us our start and end points. And now we want to set up our Dijkstra's. So our priority queue will start off with one item, which is the starting position, as well as the direction. Currently, we'll store this in DRDC again, which is the directions, the difference in row per move and the difference in column per move. We start out moving to the right, so our row displacement is 0 and our column displacement is 1. And we'll also add our set of seen states. Note that because turning is not free, we do need to keep track of which direction we are. So even if two different states are in the same cell, we still want to look at them separately if they have different if they have different directions. So long as our priority queue is non-empty, we can get the next state, which will be a row, a column, a displacement in rows, and a displacement in columns, using heapq.heap_pop, which will grab the cheapest item. One thing I did forget to add is the cost. In Python, lists are ordered in lexicographical order, meaning they first compare the first item. If they're equal, it compares the second item, and so on. So the cost does need to be at the start, unless we implement a custom comparator, but we really don't have to. Here, we just keep the cost in the first item of the state. So this will get us the next available cheapest option to look at. And then we have a couple of options. So we'll do for new cost, nr, nc, drdc, ndr, ndc in. There are three possible moves. We can move forward, which inflicts an extra cost of 1, and does not change the row or the facing direction. We can turn. Again, we note that in order to turn clockwise, this would be a row displacement of -1. This is 1 column. This is 1 row, and this is -1 columns. So if we're going to turn clockwise, we basically take a row and column direction and transform it into the column and negative of the row. We can see that this works for all of these 4 changes. So to make a clockwise turn, we don't change the position, but we do change the facing direction. Alternatively, we can turn counterclockwise, which would be the same, but instead we now keep the sign of the row and negate the sign of the column, like so. So these are our 2 operations. Notably, we swap the row and column, and we change one of the signs. It does matter which sign you change if you are trying to figure out if you're rotating clockwise or counterclockwise, but if you are going to do both anyway, you don't need to remember which one's which. For example, in this case, Swapping these two cases will not change anything, and so you don't need to go through the effort of figuring out which one is which if you don't already know. So for each of the new states, we need to check something. If the new grid position, which only really matters for this one, is equal to a wall, then we skip this case because we're not allowed to go into walls. And if this state has already been seen, then we can also skip it, because this is now the processing stage. Or rather, if we've already processed this case, that means we already found a cheaper way to get there, so we don't need to look again. But we will notably not add the case here. Normally in BFS, you would do this. However, this will not work here because this might not be the cheapest way to get to the next state. We only know that it's the cheapest way to get to the current state. And so we do need to add the scene addition here. Basically, once we've processed it, we know we've found the cheapest option. So if we find it again, we do not need to go back to it. This is necessary to prevent looping. And now we can process this. So now that we have found the next state, we add it into the priority queue using heap queue.heap push, which takes two items. The first one is the priority queue itself, and the second one is the item we're trying to add, which is going to be this. In breadth first search, we were able to exit early because whenever we saw the end state, we could just immediately terminate and not go through the rest of the queue that was equal to it. However, just like with adding to the scene state, we can also only do processing outside of the loop. So we can only check for that here. So we can do if grid RC equals E. Alternatively, we could also do if RC equals EREC because we found that earlier here, which I'm actually going to remove so that we can do this. If we have found the end state and actually determined that that's the cheapest way to get to the end state, then we can print out the cost and break. And yeah, this code is a bit slower than I remembered it being, but yeah, that is the solution for part 1. Looking at part 2, we want to figure out where the best spot to sit is. Each non-wall tile is equipped with a place to sit, and there are a couple of factors to determining what the best position is, but the most important one is whether you can actually see the path through the maze. Obviously, you want to sit somewhere where you can see the reindeer. If you sit here, you're not going to see anything, even if it's comfortable. So we're going to need to determine which tiles are part of any best path through the maze. So for example, in this example, we can see that there are a couple of paths that you can take that have the exact same cost, which means that we're going to need to extend our Dijkstra's a bit. So finding the whole path is actually a very common thing in graph theory. Basically, in order to do that, all you need to do is just keep track of, for each node, which node did you arrive there from. And then once you get to the end, you just backtrack using that map. However, because we need to get every path, we also need to backtrack for each node what is every possible way to get there in the minimal amount of time, or cost, whatever our metric is. So we're going to need to modify this code significantly. Firstly, what we're going to do is scene is going to instead be lowest cost, which will tell us the lowest cost to get to each state. And we're going to need a backtrack map, which will map from each state to all possible states that could get there in the cheapest cost. We also no longer want to exit as soon as we see the end state. Rather, we need to process all possible ways to get to the end state that are the cheapest possible, meaning we also need to keep track of the best cost overall. So what we're going to do now is, instead of breaking right away, we will only break if our cost is more expensive than the best cost. So if the cost is worse than the best cost, that means that we have gone past every way to get to the end as fast as possible. So now we can break. Otherwise, the best cost equals the cost, and we can just continue moving on with our lives. Another thing we need to do for the processing step here is we need to add stuff to the backtrack array. So what we're going to do here is we're going to mark this state as seen, but instead of seen, we're going to indicate its lowest cost. And what we're going to also do is if this cost is worse than the lowest cost to get to this state, then we will quit and ignore this case. Because do recall that the first time we add a case might not be the best time. And so when we add the best case, eventually we'll process this one first. We will indicate that it is the lowest cost. And then when we get to another way to get to the same state that is objectively worse, we will notice that and skip past that method. And then once we've found that we are out of ways to get to the end in the shortest cost, in the least cost possible, we can quit this loop and move on to the end processing stage. We're going to continue most of this to be the same. If cost is greater than lowest cost for this, then we don't want to add it. Note that we can process this twice. Basically what's happening here is if the cost is worse than optimal, we don't want to process it. And if we've already processed this state and found the best way to get there, then we don't want to add anything that's worse. This check is not strictly necessary as long as we have this one. But this step is necessary because we might still add a worse state earlier. This one saves us a bit of time by avoiding adding unnecessary options. This one is crucial to the operation of the program because it filters out the suboptimal cases. Also, we do want to note that lowest cost doesn't necessarily start with each value in it. So we can initialize each lowest cost as infinity, meaning that the first time we see it is going to be added. Actually, I think Python has a better way of doing this. Anyway, Python does have something that allows you to initialize a dictionary with defaults, but I don't know how to use it, so I'll leave that as an exercise to you and something that I will look into after I record this video. So basically what we're doing here is if we don't already have a lowest cost, that means we haven't processed it yet. So we don't know if it's optimal or not. So we're just going to have to go ahead and add it. Using infinity as a placeholder here guarantees that the cost is not going to be greater than it. And so now what we need to do here is if we're processing beyond this point, it means that this is the best possible way to get to this state. And so we're going to have to backtrack from our previous one. So this is where things get a bit tricky. Once we are here, we don't know how we got to this state because we didn't insert that into the priority queue. So we're either going to have to add it here or we're going to have to process the backtracking here. I'll show both examples so you can kind of get an idea of the options you have. But I think processing here is better because it avoids adding unnecessary items into the backtrack that you'll have to remove later. And I'll explain why that is in a bit. So what we're going to do now is we're going to basically add RC, DR, and DC into the state that is pushed into the priority queue to indicate how we got to this point. In order to avoid breaking our unpacking here, we're also going to need to add that here, but there was no previous state, so we'll just put in 4 nones. And then here we'll give it the last row, the last column, the last displacement of row, and the last displacement of column. Once we get here, we know that this is an optimal way to get there. So we're going to say if RC DRDC is not in the backtrack map, we'll initialize it to an empty set, and then we will add it there. And so now after this loop is finished running, we have processed all optimal paths and determined every possible way to get to each state that is cheapest. So we'll get some big thing like this. So for example, let's look at an example at the top of this. This tells us that to get to 15,101, we had a previous state of nothing. This makes sense as that's the starting position. To get to 15,1 facing up, the best way to get there was from 15,1 facing right, which makes sense. We start at the start position and turn left. 15,110 is for turning right, but that doesn't really matter. The best way to get to 14,1 facing up, which is the space above the start, is from the start position while facing up. Likewise, the best way to get to the space above that is from the space below it, so on and so forth. So this now tells us all of the optimal ways to get there. And we note that some of the cases will have sets with more than one item in them. I don't know if I can find a good example. Oh yes, here. So in row 9, column 15, which is this cell here, what this is saying is basically to get to this position facing up, we can either get from that, sorry, this is facing left. To get here facing left, we can either get there by first facing up and then turning, or by first facing down and then turning. Now, neither of those operations make sense, but this is just an example of a state where there are multiple possible items in the backtrack. The second way we can generate the backtrack is instead of tracking the previous position in our heap, we instead just put stuff into the backtrack here. So I'm going to first obtain the lowest cost so that we don't have to calculate this twice. And so we maintain that if the cost is worse than lowest, we obviously want to skip it. Now, if the cost is best than lowest, what that means is we've found a better way, so we need to dump the backtrack. And then if the cost is, if neither of these two are true, then that means that the cost is equal to the lowest, which means that we can add it to the backtrack. Technically, we could write this out something like this, where basically if the cost is cheaper, that means that we found a better option, so we want to dump the backtrack and add it in. And if it's equivalent, then we just want to add it as an equal option. But of course, because this line is duplicated, we can just take it outside of the if statement. Something else neat we can do here is if we are dynamically checking and updating the lowest cost, then we can initialize it here instead of here. The reason we previously couldn't initialize it here is because we couldn't be sure it was the best cost, but now we can dynamically update the best cost as we go. So we can do that. Also, sorry, this is meant to say new cost. So now we can do that, which does also prevent us from adding worse options because we're able to preemptively cull some of the options. The reason we can't use scene is because we don't know if the scene set will tell us that it's the best, but now that we're actually tracking the lowest cost, we can do that here. The reason you usually don't see that done and you usually just see a scene set that's updated in the processing stage is because it's usually just not worth it to actually track the cost. But in this case, we do actually need to track the cost. And so we're going to do it this way. And so we will end up with the same backtrack array or backtrack map like so. And now we just need to figure out what all of the possible paths were. So we're going to go through our backtrack, but in order to do that, we first need to figure out what state we ended on. So in order to figure out the end states, I'm going to maintain a set and just add all of these states. The end states only includes the one facing up, which basically tells us that the best way to get here is to go from the bottom. There are no optimal ways to get there from underneath. However, if we look at the second test example, where oh no, this is going to be the same, isn't it? No, this already is the second example, sorry. If we look at my input case, we can see that it tells us that the best way is from the left moving to the right, which makes sense because all of the other squares surrounding it are walls. Unfortunately, none of the examples show any cases where there are two optimal ways to get to the end from a previous square. But if we were to look thoroughly enough, we could find one of these branching points, but I'm not going to bother for the purpose of this. So now that we have all of our end states, which for your input could potentially be more than a single list, we're going to need to backtrack from there. So we're going to get all possible states, which is going to start as both a set and a queue. Basically what we're doing here is we're just filling out the entire backtrack. So let's suppose we had a state that looked like this, where the arrow indicates that that is a possible optimal way to get there. Then when we backtrack from this point, we're going to look at all possible ways to get there and add those into our queue. This one would add this one, but we've already seen it, and so on and so forth. In order to avoid exponential blowup from looking at cases multiple times, we need to use a set to track what we've already seen. But in order to make sure we go through all of those cases, we also need to use a queue. This is basically a breadth first fill. We are doing a breadth first fill within a Dijkstra's. You could maybe use DFS, but I think you would run into a stack overflow with the size of this grid. So relative to Dijkstra's, the breadth first fill is going to be extremely simple. And then we can just do for wall states, RC, DRDC, or rather, in this case, we no longer care about the unpacking. We just have a map from each node to its predecessors. So we can just say key equals states.pop left, and then we can say like for last in backtrack from the current state. If last in scene, we skip it. Otherwise, scene.add last and states.append last. This is just very standard breadth first fill. And finally, we now have a list of all of the states that were... I did forget one thing. The start position will not have any predecessors. So now we will have a set of all of the positions that we've seen, including the rotations. Of course, the rotations don't matter, so we're going to make a new set that only contains the row and column itself. And this will be the set of all positions that are relevant. And so we can take the length of that. Which will give us our answer for part 2. Given the complexity of today's problem and the fact that my explanation may not have been the most clear, I think it's worth taking a short recap of what we've done here. So basically, this was the input processing step. We just found the start position. Here we initialize 5 variables. The priority queue is used to determine the next possible option that we know we can get to, the next cheapest option rather. This is a map that tells us for each state what the lowest cost is to get there. Backtrack is a map that tells us that will eventually give us for each position all of the previous states along the path that could have gotten us there. Best cost is the lowest cost in order to get to the actual end of the race itself. And end states is a list of all possible states that could have gotten us to the end. The reason it matters is because of rotations here. So long as the primary queue is not empty, we grab the next possible state that we can reach. If this state is worse than lowest, then we ignore it. If the state is at the end of the grid and is worse than the best cost we found, that means that we've exceeded all, we've already processed all of the best ways to get to the end. All future states are inferior, so we can break out of our loop. Otherwise, we update the best cost and add this as one of the possible states that we could end up in. Otherwise, we loop through each of the possible procedures, which are moving forward, turning clockwise, and turning counterclockwise. If that would run us into a wall, we skip it. Otherwise, we check what the lowest cost to get to the next state is. If this method is worse, we skip it. If this method is better, then we dump the backtrack and update the cost threshold. And then we add this current state as one of the optimal ways to get to the next state. If we end up being wrong and this is not optimal, it will get dumped here. And finally, we add it to the priority queue. We add the next state to the priority queue so that it can be processed later when we get to it. After this loop, which is Dijkstra's for all paths and not just one shortest path with backtracking computed, we now have the backtrack map, which tells us for each state what all possible ways to get there were. We look at all of the end states as the beginning of our flood fill, and then we just flood fill. For each state, we look at all of the ways that we could have gotten there and add them into a set. And finally, with the set of all states that are along the path, along any optimal path to the end position, we get rid of the directions such that we only have the actual cells themselves, turn it into a set to remove duplicates, and count the number of tiles that are along any optimal path in the race. And so that is the solution for today's part 2. Thank you for watching. I hope this video mostly made sense, and I hope you enjoyed watching, and I'll see you again tomorrow.